ready to get started. And today we have some extra guests here. This is our final day of fellowship interviews. So we've got 7 able candidates in the back. I already gave them a job to do, which I thought that was a good way to orient them to the program. Told them to turn the lights off after the introductions. We'll see. It's 2, right? We just learned. Okay. So it is my pleasure to introduce today's speaker, Dr. Edward A. Fisher. He's a graduate of the NYU School of Medicine and has an impressive and distinguished career in which he is focused on lipid lipoprotein metabolism, as well as atherosclerosis and its regression and imaging. He's developed exciting animal models of atherosclerotic regression, discovered the major degradation pathways of ApoB that regulate VLDL production by the liver, and has uncovered surprising cellular plasticity of macrophages and smooth muscle cells in atherosclerosis. He and his group have also adapted HDL and other nanoparticles to deliver imaging and therapeutic agents to plaques. For his seminal work, he's been the recipient of continuous funding from the NIH and other agencies and many awards, the most recent of which is the 2019 Distinguished Achievement Award from the American Heart Association, which is the Council's highest award. In reviewing his CV, I was perhaps most impressed by his record as a lifelong learner. I mentioned that he obtained his MD degree from NYU, but he also has an MPH in epidemiology from the University of North Carolina, and a PhD in biochemistry and nutrition under the mentorship of Dr. Jan Breslow from MIT. Those were all pursued earlier in his career, but in 2010 he received a master's degree at the University of Oxford, and as recently as March of this year, 2019, he completed a bioinformatics training course at Oxford. At Cambridge, sorry. Okay. You have to respect someone who keeps pushing his own envelope so that he can continue to perform cutting-edge science and apply that to the treatment of human diseases. I have known Dr. Fisher since his days here at Mount Sinai as Professor of Medicine and Director of Lipoprotein Research. He was recruited away to NYU, alas, in 2003, where he, I guess, has been happy because he remains there. The Leon H. Charney Professor of Cardiovascular Medicine and Professor of Cell Biology. Ed, we're delighted to welcome you here today.
I knew I'd see some familiar faces, including my dean when I was at Mount Sinai. There are many, many connections in this talk with my time here and lasting influence, as I'll try to point out, with different people working on these projects. The imaging and the HDL, for example, which I won't get into, was a project with a very junior faculty member, Zahi Fayyad, who has risen to become an institute director here. He was a wet behind the ears assistant professor, Valentin Fuster, who was both of our boss, said, maybe you and he can figure out how to image plaques in mice. And so our first paper was in 1998 for the cover story in the journal Circulation. So that was a good start for his career. Certainly a good collaboration that's still going on. It's still funded. And in fact, after this, I have a meeting over in the Hess building with some people in Zahi's group. I also want to say hello to my friend Nancy Tarlin, who's at Elmhurst. I said I would make sure the slides were loaded so she could see the slides besides just hearing them. I saw her yesterday. So all of the work that I'll go over today actually definitely is Sinai-centric, and it's just a statement of fact. I'm not being patronizing because I happen to be here. It's a statement of fact because I did not work on atherosclerosis of any type before I came here. I actually worked on the ApoB VLDL metabolism and did well enough to rise to a full professor here. But because of the generosity of Valentin Fuster's starter package, and my proximity for 2 years to Jan Breslow's lab, who was my PhD mentor, but I never worked on mice for atherosclerosis. When I was with him, I actually did a clinical research project. I decided that I was going to go off in that direction because I had justified the VLDL and LDL work as these particles cause atherosclerosis. So I might as well now with startup money, best kind of money, you don't have to apply for it, right? To go in that direction. And so that really led to all the work that I'll show today. And so when I started this, the mouse models, so Dr. Fuster, who, as you all know, works very quickly because he does so many things. When he read my CV, not nearly as well as Alice, okay, he sees Breslow's name and he assumes I'm a mouse guy. Okay, one of my friends says MD, mouse spot. He seems I'm a mouse guy because I work with Breslow. So when I came to Mount Sinai, people would come up to me and say, "Oh, you're the mouse guy." I'd never worked with mouse before, ever. The stuff we did on VLDL was in rats because they're bigger livers, bigger blood volume. And so I remember going home and telling my wife, I need to start working on mice before Dr. Fuster finds out. Because then I was a untenured associate professor. I still needed his support to get promoted. I bet everyone who calls me the mouse guy have to mouse work. And so that's that probably did catalyze some. Let's get going on the mouse work and atherosclerosis. So when I started in the late 90s, early 2000, people were already using mouse models to go in this direction. There's a relatively normal coronary. There's obviously in the middle one with an advanced plaque with cholesterol crystals. There's a necrotic core, some stenosis. And on the right is, of course, what Dr. Fuster is most known for, the ruptured plaque, the vulnerable plaque that ruptures. There's a blood clot occluding that is this. Is occluding the.
Ed, you can put it up on the podium. Put it up.
Okay. Thank you. And that's someone who died of a myocardial infarction. Click that and it goes. Yes, I still do this. Right? Oh no.
Just click the mouse. Click the mouse. Anywhere? Mouse. Left.
How about next?
You can do next.
Okay. Maybe it's the left button. So, this was a crowded field. There are hundreds of labs around the world using the mouse models. After the ApoE knockout mouse of Breslow, shortly after Brown Goldstein published the LDL receptor knockout as an animal model of familial hypercholesterolemia. So people were studying progression. I got trained, actually, Don Smith is here. Valentin Fuster sent me over to apprentice with Don over on 96th Street in the clinical practice to learn some preventive cardiology. And so, which I continued. Actually, I started and ran the program at NYU up until this year, where I transitioned it to Jeffrey Berger, who's a terrific platelet thrombosis cardiologist. But that's another debt I owe. Don was a very patient, very good teacher. And because of my clinical interest, we all know, and you all see patients certainly with risk factors for cardiovascular disease. They usually come for treatment of their risk factors when they already have a big plaque burden. Not just diabetics, which we'll talk about a lot today, but non-diabetics as well. So I thought that as good as the goal is to stop the progression of the disease, the best time to fantasize about your research is before you start any of it. Okay? Francis Crick, one of his many witty sayings was the best way to ruin your hypothesis is to do the experiment. Okay? So the most fun time is, right, is contemplation. And I thought, well, that's fine. Let's just get rid of plaques. Let's try to shrink plaques. There were no good mouse models there was only one problem. There were no good mouse models for this back in the late 90s. And actually another thing that I owe to my time at Mount Sinai, I'm thinking, well, gee, this would be a good area to get into because it's important, it's relevant, but it's not overcrowded. Well, the reason it's not overcrowded was because there weren't very good models. So I needed a model. And so I went to a lecture at the Lifelong Learning. It's true, and as all of you know, who are successful scientists, it's frequently a real stimulation to go to a talk in a narrow field, and you get enriched all the time. So I saw that there was a young surgeon, Charney, I think he's now up with the VA, doing general surgery, but he was a junior faculty member who had done a fellowship in Switzerland at one of the great immunology institutes on transplant rejection, which of course, the arteriopathy of organ rejection. And I went to that, and he's talking about his animal models where they use different strains of rats or mice to take an organ from one to the other and study the concentric hypertrophy of the smooth muscle cells. And I'm sitting there thinking, at some point I stopped listening to his talk, but because I said, wait a second, if you keep the strain of the animal the same, you can transplant arteries, organs, whatever, and you won't have this transplant rejection. So that led to our first model of regression, which was an aortic transplant model, which is, I don't have this in chronological order, this model, and to illustrate some point later in the talk. Even though we don't use it as often because it's a bit cumbersome, it turned out to be very, very effective. And what we do is we harvest flax from ApoE knockout mice or other mice as on this chart, and we transplanted them, physically put them in line in a recipient mouse that was wild type. So we go from a cholesterol of 1,000 milligrams per deciliter to one where it's 50. So a very extreme, rapid, abrupt change. And we reason that if we're ever going to see anything, it's going to be under those sort of drastic conditions. But when I went up to Ernani at the end of his talk, and I told him about this idea, and he was enthusiastic and said, "You think you can get this going?" And typical surgical bravado, oh, piece of cake. Well, it took about 6 months. There were lots of practical hints, or not hints, things like the heating pad, the light, how the heating light, the distance when you anesthetized, you have to clamp the aorta, how long can you clamp, when you give anticoagulants. But it then worked out to be a fairly routine procedure. And again, another Sinai connection is that he taught a Chinese surgical research technician who's still here, Jinwan Lu, and I think he works in the transplantation program. He actually comes down, he's here, he moonlights on weekends to do, when we have to do aortic transplants now at NYU, so I'm still very well connected with him. So that was our first model. I'll show you some examples, but we've done a number of others, and a lot of this has been, until recently, with the diabetes, you'll see some changes in our perturbations, but a lot of them were lipoprotein-based because that was my background, PhD in lipoprotein metabolism. But we've used, as you'll see, our first diabetes paper was in the journal Diabetes, using the reversa mouse. But we've also done just a simple diet change, which takes much longer, going back to chow, and I'll show you an example at the very end of the talk with that. We've introduced the LDL receptor back into LDL receptor to knock out mice with adenovirus, with my colleague Catherine Moore, who co-discovered something called MIR33, which regulates cholesterol efflux and HDL metabolism. We treated these mice with this agent, anti-MIR33. We've also infused HDL, leaving the mice hypercholesterolemic, and I already mentioned this. More recently, we've published one with Ira Goldberg, another Sinai connection, did his fellowship in endocrinology here. He's our chief endocrinology at NYU now after a little detour of 20 plus years at Columbia, but he's not at NYU with one of my colleagues. We published with him this model in which we can use antisense oligonucleotides to make any mouse LDL receptor deficient. So this way you don't have to do a lot of genetic crossing. If if you have your favorite factor already knocked out or overexpressed in a mouse, you can make them hyperlipidemic very convenient. Okay, and then when you withdraw the beta cell, the LDL receptor comes back, and you can accelerate that by giving a sense oligonucleotide, which soaks up the antisense to allow the endogenous RNA to be translated right away. We've also used PCSK9, and you're all familiar with PCSK9, the antibodies to PCSK9 lower LDL, so if you overexpress PCSK9, you raise HDL, and then we can use an NTP inhibitor or other strategies, but again, same idea. We can start with any genotype of the mouse, raise LDL, and lower it. So now more people are coming into this field that really the pioneering studies have done here. And these are results from when I was at Mount Sinai. What we saw, CD68 is a common marker for macrophages. This is a mouse aorta in cross-section. You can see the brown staining indicates this is a macrophage-filled plaque. And here's the lumen. And then if we take one of these plaques after this is at about 16 weeks of the diet feedings, they give that complexity. Similar, very similar to the plaque in the center, first picture I showed of people, from samples from people. And if we, as you can see here, there's, I don't show you the full picture, but if we go back into an knockout recipient, that's a control for the surgery, the anesthesia, etc. The plaque continues to grow over the next few weeks. But if we go into a wild-type recipient where the lipoprotein profile is enviable, if we had Don Smith had patients with HDLs of 65 and LDLs of 40, he'd be very happy. Okay, and so this environment in mice does the following: no macrophages after 4 weeks; they're gone. So we wanted to know why, and one way to approach it was to try to get some molecular information. So in 2002, another study from Mount Sinai, this was the first use of laser capture microdissection in vascular biology. I had a very bright graduate student, Eugene Trogan, who got his PhD from here, this is some of his work. He had noticed we were talking about how we're going to figure out how these macrophages disappear. We were talking to Gwen Randolph, who's another junior faculty member in immunology, who now is at Washington University. And she had worked with Ralph Steinman, who discovered dendritic cells, won the Nobel Prize a few years ago. Well, just made it, as some of you know the news story. He died on Friday, but the committee didn't know. He got the prize on Monday. But in any case, dendritic cells are very migratory. So we went to her to see if some of this disappearance could be from cells leaving, and they do, and we demonstrated that in a beautiful paper with Glenn. But we wanted to know what was being reprogrammed. So I call this plaque whispering. What we've done, and now we're doing single cell RNA, we're going all the way, I went to the bioinformatics course at Cambridge. Me and 18 Cambridge undergraduates. There was not a single one asked me, since it was because they're English or British, or criticism. Not a single one asked me what I was doing in their class. The instructors got spooked. They thought, I think, that I was sent by the dean's office to check up on them. But now we're interrogating with, or listening, I should say, with all the elements that can be applied. Because I said, well, we have models in which the plaques are healing, they're getting better, they're resolving. Let them tell us what's going on, rather than impose. Let's manipulate this gene or that gene. I have a system now, a model where the plaques are getting better. Let's try to figure out how that's happening. And so, to get some molecular information back in 2002, we didn't have single cell RNA-seq. We didn't have even RNA-seq. It was Affymetrix, microarrays, and PCR. So we did our study in which we pulled out of the plaques with the laser capture microdissection the macrophages. We were quick stain, non-denaturing, and pull up with an LCM instrument that the first one we used actually was a Sloan Kettering and then Paul Klotman. And thought idea, there's a name that some of you remember. He actually believed that this project could go somewhere and had the Department of Medicine buy the first LCM assignment so that we could use it, other people started using it as well. And so by doing that, what we avoided was exactly what the cancer biologists developed this for. We didn't just grind up the whole plaque and have a mixture of RNA from every single cell, because that's like V8 juice, right? You can't tell any vegetable in there, except maybe tomato, because it's still pinkish. You know that that's in there, but what are the other 7? They say 8 great vegetables, right? So that's what happens when people were doing some molecular biology on plaques. They take the whole aorta and they would just grind it up. So we thought, well, we want to know what's going on in those macrophages, since those are the cells that disappear. And everyone acknowledged historically that they're central to the pathology. So we pulled out the macrophages and did a microarray. And so bioinformatics was not merely, it's an evolving field, and so you can imagine back when we were doing this 10, 15 years ago, we had, unfortunately, 2 different bioinformaticians who had totally different algorithms. Each one was a partisan of and gave us different candidates of important genes. And while they were arguing over what pathways were important, we did sort of common sense. What went up the most, what went down the most. Okay? So what do we know, right? We said the Excel spreadsheet. And it turns out what went up the most, I can't go, well, there are 2 things. If I go back.
Yeah, you used to.
Exactly. There are 2 points here. Put this here. Wireless, yeah. Modern technology. So what you notice here, so if we pull the cells out from progressing and regressing plaques, you can see that the pattern of gene expression is radically different. And these are the genes that go down, these are the genes that go up in that color. If you line them up, not everything that went up during progression goes down in regression and vice versa. It means already an early hint that new pathways have to be invoked. Sort of like, I like the idea of New Year's Eve in Times Square, all the kickers take beer cans and whatever else on the ground. When everyone leaves, they have to bring in a whole cleanup crew, a whole new pathway to take care of them. So to resolve a plaque, it's not just rewinding the tape. For those of you who remember what tape is, but I still listen to tape. So that's one lesson from this early study, that the regression is not just the reverse of progression. And then if we looked at what was all the way on the extreme, the gene that was most upregulated was arginase 1. Now, my PhD is in biochemistry. I studied intermediate metabolism. I knew of arginase 1 as the urea cycle in the liver. So I said to Eugene, sure we didn't screw something up, like when you took the sample, you didn't hit the liver or something like that. No, what did I know? Because M1, M2 cells hadn't been described by Simon Gordon and Alberto Mantovani until the late 80s, sort of like dendritic cell with Steiner. I took immunology in the mid-70s, so I never heard of these things, these M1 and M2 macrophages. But when I go to PubMed, thank God for PubMed, go in arginase 1 and macrophage, right away, a zillion articles come up. And what you see is that it is a marker. It's taken as a standard marker for the so-called M2 macrophages. And so this is a very simplistic classification. There are so many subtypes. It's like the T-cell world. There are 20, 30 different types of macrophages. And we've contributed to this phenomenon as well through single-cell RNA-seq, which always shows a lot of heterogeneity within a cell. The M1, though, are familiar to you as the activated inflammatory cells. They make TNF alpha, IL-1 beta, IL-6. They're low in anti-inflammatory factors, IL-10 in particular. Whereas M2, which I like to call tissue remodeling, but they're also wound healing, They make a lot of IL-10. They don't make a lot of inflammatory factors. And arginase 1 has a putative functional role, which we won't get into, but it's certainly taken as a marker. But just as we'll come back to actually towards the end, that most people feel that part of the problem in wound healing in diabetics is the lack of their macrophages to become M2-like and resolve the inflammation and to remodel the tissue. So it already was a connection with diabetes just from the early studies in macrophage phenotype. So these are other markers of the M2 state, arginase 1, mannose receptors. And what we see in those cells that were plucked from the regression environment, that they all were elevated. So it wasn't just an isolated hit on arginase 1. They actually have an enrichment in the phenotype and the signature features of an M2 cell. So that led our attention to where do these come from and are they really required? Okay, in the non-diabetic, you'll see this is a good introduction, at least I think, my own humble opinion, a good introduction to the diabetes work that I'll show you today. So from a review from Frederick Geisman, who's now at Sloan Kettering, was a star fellow with Dan Littman at NYU that went to Europe, built his career, and he got recruited back. He and others have shown that they didn't show that there are two major subsets of monocytes in the circulation. This is the mouse nomenclature. The human nomenclature is different, but humans also have these two basic subsets. And these LY16 high cells, which are here, are thought to be the precursors after they're recruited into inflammatory sites, inflamed sites, of the M1 type. And the LY16 low are thought to be the precursors of the M2 type. So it's known what chemokine receptors on these cells are required to get them from the circulation across the endothelium into the tissue. And I'll show you the sort of nitty-gritty and not the complete story that we worked out. But we used CCR2 knockout mice to eliminate the possibility that these LY16 cells would come into the plaque and to see what effect they had on regression and the ability to enrich in the M2 state. This was actually, we thought, would be the sort of the negative control experiment because, again, if you look at this paradigm, we should be interested in this, okay, and not this because these become the M1s. And so I'm showing you this because the result was the negative control turned out to be the positive result. So we did this, we went back to the aortic transplant model where we grew plaques in the knockout mouse, took out the aortic arch, and then Dr. Drew stitched them in to below the diaphragm. Why did we go below the diaphragm? Because we did imaging with Zyme of these mice to show by MRI you can follow progression and regression non-invasively. And you can only use MRI in mice with vascular imaging below the diaphragm because of the respiratory movement. So this worked out very nicely and get an anatomical landmark as well. I won't show those images, but we published them with Zyme that you can indeed follow the progression of the plaque non-invasively. Okay, now in the CCR2 knockout mouse, that means all the circulating monocytes don't have CCR2. Again, the lipid profile is beautiful. Again, in Dr. Smith's clinic, he declared victory and see the patient just once a year. But what we saw here is summarized, and actually here's two more current sign-on connections. Krishna Raman is a resident in medicine in the Mount Sinai program, first year, and Yulia Van Gruyet, when she finished in my lab, she's a PhD, she did her postdoc and started this project. She took a junior faculty job in cardiology and research, and is an assistant professor of medicine here at Mount Sinai. So these are current connections with Sinai. So when we did the experiment and started off with these baseline plaques in the knockout, we saw what we expected: lots of macrophages and not much evidence of M2-like state. We're using the mannose receptor because Mouse receptor is also used in a lot of human studies, clinical studies for M2 state. So we're using the same marker that would be used for human clients. And then, not surprisingly, when we take that plaque and we put it back into a knockout mouse, we see, if anything, there's a little expansion of the macrophage population. There's still not much in the way of the M2 enrichment. Now we go into the wild type. Again, we get the result that we've seen before. We have a decrease in the macrophage population and a large increase in the staining for the M2-like state. So this was a surprising result. When we used the CCR2 knockout mouse, and we demonstrated that cells were coming in. The reviewers this took probably a year and a half to get accepted because of a number of technical points the reviewers wanted us to address, and we had to repeat essentially the whole study to get the material. So it took a while, but it was successful. And what you see is that actually there is not much of a regression in spite of good lipid lowering, and not much of an enrichment in the M2 state. So what we did was really prove, at least in this context, that the precursor of these M2-like cells can come from the so-called inflammatory monocytes, the LY6 high. There are a number of examples of this happening in different diseases, inflammatory diseases. So, but we were among the first, and certainly we were the first in atherosclerosis research. Now, is this true, unrelated? To show that this was required, we used a genetic trick. Mice that were deficient in the factor STAT6, which is required for the M2 polarization. Other people have shown that. And if we do that, if we use mice that have monocytes and then become macrophages and don't have the STAT6 pathway, they cannot, even with the appropriate stimuli, become M2-like. And what you see is that there is less regression than in the control, and there's not, as we expect, there's not much enrichment in the M2 state. In fact, a factor that's the M1 state, MCP1, it is actually high. And so these cells remain in the activated inflammatory state. And so you need this M2-like pathway, this polarization pathway to get good regression. And this might, you look for clinical, when you're a mouse doctor and sometimes you're a medical doctor, obviously you look for connections between the two worlds. And although sometimes humans are not great models for mice, just around, sometimes there is evidence that is consistent, as you'll see in the diabetes part, which is about to start, the next phase. But just to point out that the CANTOS trial, which was big news, came out, about 2 years ago, that it showed that just lowering LDL aggressively did not give full benefit in terms of, this was an event trial in the major adverse cardiovascular event rate, until you also addressed the inflammation. In this case, it was an antibody against IL-1 beta. So I think what our mouse work shows is that you need to have a inflammation resolving environment to get the maximum benefit from the lipid lowering. So in that, they agree thematically. Now let's talk about diabetes and atherosclerosis, that introduction. And you'll see why I gave you, because you need to know what's going on in the non-diabetic before you see the content. So very informed audience, so I won't belabor the point, but heart disease is the leading cause of death in people who've got diabetes. And although the majority of diabetics, of course, again, as you know, are type 2, this is also the leading cause of death in type 1 diabetics as well. And so we have looked at the clinical literature to get little talking points. This is just one study, but did have a combination of 26 trials, 170,000 participants, just to make the point that you can be misled by the superficial interpretation of clinical results, which are usually given as relative risk reductions. Okay, how many times have you heard a statins lower events by 30%, 40%, whatever. That doesn't tell you about the absolute rate. And so diabetics, pre-diabetics, metabolic syndrome, they're known, as you all know, to have higher risk of coronary artery disease, depending on the survey, 2 to 4 times. Okay? So when you lower them by 30–40%, you still have this increase in absolute risk versus the non-diabetics. This is shown here. Yes, you have this 25% reduction from 6% to 4.5%, but this 4.5% and 4.2% in type 2 diabetics is higher than the 3.2% in the non-diabetics. And this is just one study. Some show even bigger differences in the gap between the diabetics and the non-diabetics. So diabetics do not respond as well to conventional lipid-lowering therapy to lower their risk to the absolute level in non-diabetics. To me, that's a crucial point. There are not a lot of imaging studies, but there are. This one was directly from Japan, focused on imaging. But in some of the IVA studies that were done by Steve Nissen and their colleagues, in post-hoc analyses, they did break out diabetics, non-diabetics, people with low HDL, high HDL, a series of papers, and it substantially agrees with this smaller study. Here are diabetics, non-diabetics. They have a lowering of their LDL to equal degree by statins, okay, 35%. And this is over, I think, a year or two. You can see that the non-diabetics have this much reduction in plaque volume versus the diabetics. So there's an impairment of the regression of the plaque in spite of equal and successful LDL lowering. So we wanted to start to have an animal model to replicate this and then look at the factors. Yes?
What were the LDL levels for this drug? I'm just curious. What was the target LDL?
These were not, this is before,
For the second phase, yeah.
you know, you get down to 40 or 50.
Okay.
These are probably about 90, 80 to 90, so, yeah. And so we took one of those models that I mentioned on the table, not to expect you to remember them all, but this was the reverser mouse, developed by a colleague at UCLA, Steve Young. But this is a genetic model in which you have LDL receptor knockout mice, the model of familial hypercholesterolemia. And it has a genetic switch where you can turn off the MTP gene in the liver. The MTP is required for VLDL assembly and secretion. So I like this model because it connects with my lipoprotein world. And what that does, when you throw the switch, then you shut off the production of VLDL, and VLDL becomes LDL. So you shut off the production of LDL. And that's shown here. This is an FPLC profile. This is before the switch is thrown. All of this is the LDL peak in the mice. And all of these down here are the mice in the different groups after the switch was thrown. So you can let plaques grow. Now we don't need to do the surgery. You let plaques grow, you throw the switch, and then bingo, they have normal cholesterol levels. At the same time we throw the switch, we give these mice STZ to cause type 1 diabetes. And that far and away the mouse world, as Dr. Brownlee knows, has been the more studied mouse. So we're starting to go towards type 2 in our own lab, and I'll show you an example in a few minutes. But so now what we have are two groups after the switch is thrown where they have equally low LDL cholesterols and yet, of course, the STZ, they're diabetic, hyperglycemia. And what we see, we saw what was in that clinical study. If we look at the amount of the macrophages in the plaques, starting before we throw the switch, it's up here, and then in the mice that are normoglycemic, we get this much, which is only about 2/3 of the cells are not. And then in the diabetic, which has the same degree of lipid lowering, okay, you're stuck about halfway. All the studies we've done using different models, we get about halfway, and then it just flips out. And then, so we want to know why, right? So I'll show you 4 reasons. That's the title of my talk. Insights why it might be hard to regress plaques. The first goes back, now I'm linking it to the first part of my talk, to this M2 enrichment. What you see is there's a failure to fully assume this resolving state. Here's arginase 1. So here we start off in a plaque, and then it goes up in the non-diabetic, and it doesn't really go very far in the diabetic. Now, arginase 2 is another marker, IL-10 I mentioned. You can see no matter what we looked at, and it's all in the paper, a whole table of other things we looked at, we do not fully adopt this M2-like state. And other people have published that hyperglycemia impairs the response of monocytes and macrophages to the stimuli that push this process, which is called polarization. And Anne-Marie Schmidt, who, as you all know, is at NYU, published a paper where some of this failure to polarize is related, not surprisingly, to rage, because Anne-Marie has shown rage regulates everything. It's amazing. It's every lab meeting I go to, it's just another amazing story that has sung by actually a Sinai connection, Henry Ruiz, who was a postdoc in Christophe's lab. He's an amazing guy. So, in any case, so you see, as I said before, you need this M2 enrichment to get resolving plaques. You fail in these mice. Number 2. This is based on plaque macrophage genetics and atherosclerosis. A few years ago with Catherine Moore, we had this review. What I really just want to highlight here is that if you have monocytosis, okay, monocytes are coming in like any inflammatory site and become macrophages. If you have more monocytes, forget about whether they're intrinsically more activatable or whatever their changes are on single-cell RNA-seq. If you have more of them, even if their recruitability stayed the same, you'd have more cells entering the plaque. Okay? So we wanted to know whether the failure of the reduction had something to do, of the macrophage content in the plaque, had something to do with circulating monocytosis. And so with Ira Goldberg, and I'll show a cartoon from Michael Brownlee's editorial on this article, with Ira Goldberg and Alan Tall, when Ira was still up at Columbia, we had a paper that showed hyperglycemia causes monocytosis and neutrophilia. Neutrophilia comes back at the very end of the talk to be important as well in diabetic atherosclerosis. And we've repeated, not this exact study, won't get something published in a good journal repeating the exact study, but the basic phenomenon has been reproducible in a series of publications with and without iron. What you see here is that if we look at the total monocytes, they are up, and this now we're using a genetic model of type 1, the Akita mouse, which has a failure to secrete insulin. And then if we look at the two subsets, both those high cells and the low cells go up. Okay? Now, if we use SGLT2 inhibitor, well known to all of you, of course, you will see that at the same time that we're lowering the glucose in the Akita mouse, we actually can restore these counts back to the normal non-diabetic levels. Okay? So if we now look at the entry of monocytes into those plaques, not surprisingly, then with the hyperglycemia, even though this is an STZ, and I'm showing you data with Akita, they really were equivalent, you see that there is more entry using trafficking assays we learned from one Randolph, another Sinai connection. We could directly in vivo measure how many circulating monocytes come into a plaque. They increase along with the increase in the circulating number, and when we drop that number by using SGLT2 inhibitor, you can see they also decrease. Yes?
Is something you can drop in the sugar that's causing decreased inflammation, or is it that there's an anti-inflammatory component to the SGLT2 that we don't know about?
The first possibility, right? Because we also tried it to see in the non-diabetic and really didn't see much change. I'm not showing you to you here, but yeah. There wasn't much change in the non-diabetic, and the change was more dramatic in the diabetic with SGLT2 versus the regressing. I'm not showing you that picture, but we have the non-diabetic with SGLT2 as well. So the mechanism for this is based on actually bone marrow proliferation of the precursors of monocytes and neutrophils. This is just very obviously simplistic, because the next slide is more complicated. You have the precursor cells, and they become CMPs, GMPs, monocytes, and neutrophils. And there, the hyperglycemia causes a proliferation of the CMPs and the GMPs. And we've worked out the mechanism to a large degree. Here it's from Dr. Brownlee's editorial. It's a complicated slide. I won't dwell on it in the interest of time. Just that the circulating neutrophils are stimulated by hyperglycemia to make a lot of the inflammatory factors. They work as a heterodimer S100A8 and 9. And 8 and 8-9 go into the bone marrow. This is the bone marrow here. So it's secreted from the neutrophil in circulation into the bone marrow. S100A8 and A9 are ligands for the RAGE. There's RAGE again. Dr. Schmidt is a co-author of this. And this actually stimulates the proliferation of those precursors. And so now there are more precursors turning into monocytes and neutrophils. They get out back into circulation, and then they go into the plaques and become macrophages. Now, is there any human data that goes along with this? In the same paper, we worked with Trevor Orchard, familiar to many of you at the University of Pittsburgh, and what we see in this type 1 population, if you divide them into CAD versus no CAD, they had more monocytes, more neutrophils, and more S100A8-A9, which we think is the mediator, one of the mediators. And if you do correlations between white blood cells and S100A8-A9 and neutrophils in particular, you can see, again, this is a clinical population, so the data are not going to be as tight, but there was a statistically significant positive correlation. Ira Goldberg recently published in the Diabetes Complications Journal a study he did in China in which he looked at people with type 2 diabetes who responded well to their treatment or did not in terms of their diabetes treatment, and whether or not there was a differential effect that you can see on the monocytes and neutrophils. And you can see that there is, rather than look at the table, you can see the graphs. There's neutrophils versus hemoglobin A1C, and monocytes versus hemoglobin A1C. So this, again, this is the type 2 population. So we are getting data consistent in people in type 1 and type 2 with those mouse studies. Now the third mechanism, there are only 4, don't worry. Those of you who might have to be at 9:30, I think it'll be 5 minutes each. Trained immunity, also known as immune memory. Okay, what this means is that the innate immune cells, so we all know that the T cells are adaptive. They take a while, 10 days, to start getting a response to the antigen. More immediate are neutrophils and macrophages. They are pre-programmed to respond to some threats, either bacterial or non-bacterial, some sterile threats as well, to sort of start pushing back against the attack. And what was not appreciated until recently, more recently, is that these cells actually can have some memory as well. In other words, the innate immune system, after it sees one of these insults that it's programmed to respond to, if it sees it again, it will respond even more strongly. Okay, sort of like an antibody boosting when you see another antigen. And a lot of this is thought to be through epigenetic reprogramming, changes in the DNA, the organization of the DNA in the chromatin, so that the genes that are going to respond like NF-kappa B to LPS, endotoxin. They are poised to really start up their response much sooner and much more much higher than before. So this is the rage in a lot of inflammatory diseases, the trained immunity component. Now, now colleague Robert Chowdhury, another Sinai connection, he was my fellow here at Mount Sinai. Now he's a full professor at Oxford. So he's done very well. He did an experiment to look to see if there's immune memory in diabetes using mice. Okay? And what he did was to take a diabetic mouse, type 1 again, or a control mouse, took the bone marrow cells out, which are filled with those innate immune cells. There are others as well, so it's not totally tight, but this is a standard experiment in this field. And he put them into LDL receptor knockout mice, put them on a Western diet to see what sort of clot they have. Now, these mice are not diabetic, so he's taking bone marrow from a diabetic mouse and a control mouse, putting it into an LDL receptor knockout, feed them this Western diet, get their cholesterols up. And what did he see? He saw that the mice that got the bone marrow from a non-diabetic had this much plaque, and those that got the bone marrow from the diabetic mouse had about twice as much. So he was able to transmit the diabetes effect on the innate immune system to another mouse. This is a classic experiment now with trained immunity or immune memory. So type 1 diabetes leads to a memory, okay? Now, here's a human study. Okay, say, these mice, enough of these mice. From Rama Natarajan, very well-respected researcher in diabetes. She got samples from the EDIC study, and I just put the summary here. She's looking at epigenetics, but epigenetics is a big term. If you have stored samples, you need to get something that's stable. Covalent modification of DNA by methylation is now a very useful tool that people are using to go back into their studies. 2 groups of type 1 patients, with and without complications, and then she used 2 sets of genomic DNAs, collected 16 years apart from each other. So she looked at those who went on to have cardiovascular complications and those that didn't, and she found a persistency in the circulating white blood cells and monocytes, in particular, of DNA methylation over time. And key genomic loci associated with diabetic complications provide direct evidence of a relation between DNA methylation and human metabolic memory, supporting an epigenetic mechanism for the metabolic memory. So these are clinical studies. You're going to see more and more of this type of work, and not only type 1, of course, but type 2. So this is a beautiful paper. The last part is now switching to some type 2 style research we're doing. It's related to obesity. It's funded by a program project I had with Catherine Moore and Henry Schmidt. Again, we're close to the end, and most of you are familiar with this. The macrophage is a key cell, both in fat tissue, and of course I've gone over what happens in the plaque. And it's thought that as you become obese, there's macrophage inflammation, and then if you lose weight, or some drugs like the TZDs promote the polarization back to this M2 state, which helps to resolve actually the inflammation in the adipose people. So I have a very creative postdoc out of Weinstock, and we used Ira Goldberg's model with the LDL receptor ASO. We let these mice get fat in the mouse world. That's 40 grams, over 40 grams. And they're LDL receptor knockouts, so they got plaques. So they're fat and they have plaques. Okay, now we split into 3 groups. One, we lowered their cholesterol, but we let them keep eating a high-fat diet, so they just got fatter. Others, we calorically restricted them to 70% of calories. Tony Ferrante at Columbia published a paper showing this protocol was very effective in looking at dynamic changes in fat depots. And the third group, we did both. We calorically restricted and we lowered the cholesterol. And what we saw was, not surprisingly, I'll just gloss over this, the animals that lost weight improved their glucose tolerance tests. Their HOMA-IR was better, so, and of course their weight went down. So they had the appropriate response to losing weight. Okay. In terms of their cholesterol, we had the group with caloric restriction, which is the key group that I'll focus on. You see they still remain above the line that you need to achieve to get regression. So they're still going to have a progression stimulus of cholesterol. At the same time, they're losing weight. If we look at what happened to the macrophage content in the plaque over just 2 weeks, this is just a 2-week study, you see the calorically restricted group had as good regression. In fact, there was no additional benefit when they lowered their cholesterol. And so this is about a 30% reduction in 2 weeks just from them losing weight. Okay. So we wanted to know, given this trained immunity immune member, macrophages are in the fat tissue, they're also in the plaque. Is there some signal that goes from the fat to the bone marrow to reprogram those precursors that come out to the plaque now, and they are better in terms of becoming M2-like and dissolving the inflammation? So Ada did a bone marrow transplant. Again, this has become the standard trained immunity in vivo study. And phenomenally, what she finds is that if she just takes the bone marrow out of those calorically restricted mice, she winds up, after 16 weeks of the westernized feeding, with half the plaque. So we're able to transmit some quality, some changes in the precursors of monocytes and neutrophils that were initiated from the change in obesity after caloric restriction. The last, and this is the last one, neutrophil extracellular traps, NETs. NETs are the result of the sort of the blowing up, it's not apoptosis, it's another process. Neutrophils can get activated by many stimuli, and they spew out these nets of chromatin, which also have a number of neutrophil factors, elastase, myeloperoxidase, the histones, which is chromatin, and they have a lot of anti- and pro-inflammatory features. Anti-inflammatory, for example, they can tie up microbes, literally like fly paper. But they also are known to promote macrophage inflammation in pathways which I don't have time to present, and also they're all conjectural at this point. Now, why is this relevant? In 2015, Elisa Wagner at Harvard showed that neutrophils isolated from type 1 and type 2 diabetic humans and mice were primed to produce nets, a process called mitosis, and she was studying in the context of wound healing. Nets impaired wound healing. Okay, what about atherosclerosis? We did this study. We took these LDL receptor knockout mice, and we made them diabetic, and at the time we made them diabetic and gently lowered their cholesterol. Some got an injection of DNase 1, because DNase 1 has been shown by others to dissolve this chromatin structure. So you dissolve the nets. And what we saw was really very exciting to us. Here is the group, the two diabetic groups with DNase 1 treatment without. The cholesterols are similar, the blood glucose is similar, but one, as expected, has a lot more nets than the other groups. But the DNase 1 treatment indeed reduced the nets, as you can see here. What did it do in atherosclerosis? We now went from impaired regression. Here's that impaired regression. We go from here to here, now from here to there. But if we now get rid of the nets from DNase 1, you can see that the regression is substantially restored. So nets is yet another contribution. So let me sum up. Diabetes impairs atherosclerosis. Regression in mouse models consistent with clinical data. But these four, and they're interrelated, in ways that we need to figure out with proteomics, bioinformatics. At least four factors contribute to this finding: inability to resolve inflammation, monocytosis, neutrophilia, trained immunity, and mitosis. Some potential therapies already address some of these. Okay, there's a company that Charles Rahan and Big Pharma is looking at these, specialized in pro-resolving mediators, such as dissolvents and fluorescents, that will allow getting over the speed bump in diabetes, I think, of M1 to M2, that clearly is a problem there. There are nanomedicines being developed by Willem Mulder and Zai Fayad here at Mount Sinai. They have a beautiful Nature Review paper on nanomedicines, the block train community, that are now going to be put in clinical trials in Europe. And DNA Swan actually has been used for cystic fibrosis in particular to dissolve that horrible mucus in the lungs. And people now are proposing DNA Swan to treat inflammatory diseases in which there is necrosis. And so, again, I gave a lot of the Sinai connections and already Alex are former members of the lab. Here's another, Dr. Feig, who Alex knew when he was a resident, and then a fellow in cardiology at Mount Sinai. I mentioned the faculty members, Robin was my fellow, Glenn was here, and then, of course, acknowledged the funding from the NIH. Sorry for going a few minutes over.
So Ed, thank you for actually an amazing historical and also metabolic and cardiovascular overview. A lot of this actually I didn't know about. I didn't know about this necrosis story. So I'm sitting here trying to understand how DNase can get into the arterial wall. How is it administered? How do you get it there? Cystic fibrosis, I think you inhale it last I knew. But I don't know how you give it systemically and get it into the arterial wall.
Inject it. It's just, it's easy. I don't know if it's, what is it? You know, I forget what the vehicle is. It's just injected out.
IP?
Yes, it goes all over.
But it only, does it have effects on other tissues?
Oh yeah, so people have shown...
maybe adverse effects on other tissues.
Oh, adverse effects. In the animal world, no. It actually was pioneered by Boris Grazis, an immunologist. He's a Colombian that was in Molecular Cell paper, where he showed that in mouse models of systemic lupus erythematosus, SLE, which of course has the autoantibodies like the DNA, when they inject these mice with DNA Swan, the clinical severity of the disease goes down. And then now he has genetic models. If he knocks out DNase, there are two major DNases made in mammals. If he knocks them out, the disease severity is a lot worse. So it's surprisingly benign in the mouse world. Okay, who knows what happens? Because you're right, in CF it's given
Inhalation.
just the inhalation. Dr. Brown, we have his hand up.
So critical starting point of this question is why patients with type 1 diabetes who don't have apparent dyslipidemias or hypertension or the other risk factors have accelerated atherosclerosis. So that's one question. And the other question, and that's a quick comment on you mentioned the SPM, survivor tables. Last time we talked to that, like, firm believer in hyperinsulinemia as having a major role in altering metabolism of these things in a way that makes them proactive effective. And so that's one question. The other question is, with regard to the original cell thing or the hyperglycemia doing these various things, why do you think that the effects of SGLT2 inhibitors is so modest in terms of absolute reduction in atherosclerosis and events?
Okay. Well, I think you need the hyperglycemia. So, and from work that you've done also, I said there are 4 things. There are 400 things, including increased, we show in the diabetic mouse is more oxidative stress, working with, with aldose reductase. We had a paper last year where that makes everything worse. In mice are low expressing aldose reductase. So this was not meant to be inclusive. These are just vignettes from recent work. So I think you need, for some of these complications, actually poorly controlled, poor control of diabetes that you do have hyperglycemia. Hyperinsulinemia could be, yes, another layer. And George King, working with Ron Kahn, did those tissue-selective knockouts of the insulin receptor and showed insulin resistance in endothelial cells or in the liver or elsewhere had an effect on atherosclerosis. They're coming to the rescue.
Yes,
So there's some reports of a peptide S961, which is a partial blocker of the insulin receptor. So we are now starting to use that in osmotic pump to introduce insulin resistance into lean mice, into type 1 mice, and just start using it as, let's just look at an independent manipulation, as independent as we get of hyperinsulinemia, and see what that does, because that has been a real hard thing. In the OB-DBDB world, these were models that were going to, maybe that's why Jeff Friedman didn't win the Nobel Prize this week still. No, they're great advances. But those mouse models were thought to be the foundation for insulin-resistant studies in atherosclerosis and other diseases. But the leptin knockout mouse has actually less atherosclerosis than the control. So that turned out so leptin is doing more than just causing insulin resistance, because either that or insulin resistance is actually a good thing, right? But by selectively being able to manipulate it, certainly with the diet-induced obesity, you do get some insulin resistance. But you also, the complication there is that the high-fat feeding of the diet, there was a Cell paper a year ago by Eiko Latz in Germany, that causes trained immunity, immune memory, dietary components. When Helen Villasara was here, she showed that dietary AGEs were pro-atherogenic. I was a co-author of that paper. The saturated fats stimulate the TLRs, the toll-like receptors, and are inflammatory. So there are components of the diet used to make the mice obese that can have independent effects separate from the weight gain, the atherosclerosis. So now that we're in the world of trained immunity and single-cell RNA-seq, where every study has more and more heterogeneity, because the capture rate in those techniques of cells goes up and up, so now you have more data, and now you can get the minor populations. So we're up to 13 different subsets of macrophages and plaques, for example. And the next round will be 26 and whatever. So, but going back to your question, I think insulin resistance is really key to figure out what it's doing. And there are different ways of making it too, clearly. So the leptin way of making it didn't have an effect. Actually, it was better for atherine. So, yeah.
So, two-part question on glucose in the macrophages. First, the time course of the effect, and the second part is it at the bone marrow level or later?
Well, if you take cells out, I didn't show you Robin Chowdhury in bone marrow transplant. You also took circulating monocytes from people and from diabetics and non-diabetics. Put them in culture and gave them the stimuli to become M1-like or M2-like. And the ones in the hyperglycemic diabetics, they had more response to the M1 stimulus and less to the M2 than the samples taken from the non-diabetics. So it's thought that the effects that you see in the tissue, the end organ, actually have come from cells that were altered already in the bone marrow into the circulation, into the tissue. But certainly local factors in the tissue will be operative as well. So the time course is, again, in vitro, it's hours. You can take a naive cell and just put them in a hyperglycemic medium, which we did in our diabetes paper, and show that just within a few hours they just stop responding to the IL-4, which is the polarizer to the M2. So it's quick.
I'm sorry, we're gonna have to stop now because I feel like this could go on forever, but you have a busy morning. You're gonna be meeting with the fellows at noon. And we have a busy morning because we have fellow applicants
Right.
back, so.
I'm sure there's some patients somewhere you're going to send it to.
Right. No, we pulled that off for the day. Okay, thank you.